Hello, Stats class. This is lesson 6-1A, beginning of random variables. So before we go on, I should tell you what a random variable is. We've actually been working with them before. You just may not have known that that's what it was. It is a variable, obviously you know what variables are, for which the value depends on chance. So all through the probability unit, we've been working with these, and some of my first examples are going to sound really familiar to you because of that. For example, the number of heads on a coin if you flip it 3 times. So maybe we flip the coin 3 times, we count how many heads, we write down that number, and that's my random variable represents that number, which would change every time I flip again. Maybe I'm rolling a die and the number that shows up on the top of my die is the random variable, and it could be any number from 1 to 6. Or maybe I might roll 2 dice and find the sum. So sometimes those values of the random variable are equally likely, sometimes they're not, sometimes they range. The range of values depends on the situation. Those numbers that all of these examples I just gave you are all discrete, which is what we're doing today. And then next week we'll talk about continuous. So a discrete random variable, which is what we're starting with. Notice that's ETE, not EET. Versus continuous. I think we've talked about this before when we were doing scatter plots and do you connect the points or do you not connect the points? Discrete just means there's a finite or limited number of outcomes. And continuous means there's an infinite number of outcomes, and we will come back to those. For instance, if you're looking at a normal curve, that would be a continuous random variable. But discrete is what we're starting with. Usually we'll be working with whole numbers only for the values of our variable, such as 3 heads out of 3 or something like that. And then, of course, then we have the probabilities, which are not whole numbers, they're decimals. And the discrete ones, we've done this before, that basically the probabilities of all the possible outcomes add up to 1. So we're still talking about probability distributions like we did in chapter 5, and we're just going to take it a step further. So the first step further we're going to do besides vocab is talk about how to find the average or the mean of a random variable. So that would be the mean of all possible values. So let's do an example with the 3 coins. And with 3 coins, we could get heads, heads, heads. We could get heads, heads, tails. We could get, I'm just going to list them all, heads, tails, heads. We could get tails, heads, heads. We probably want to group these ones together because those are the ones with 2 heads. We could also get 2 tails and a head. So head, tail, 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 head, tail, 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 head would be the 3 ways to get 1 head. So 3 heads, 2 heads, 1 head, and then last but not least, we could get 3 tails, which would be 0 heads. So those are my possible outcomes for the random variable x, where x represents the number, I should have told you this first, the number of heads in 3 flips. And x could be 3, 2, 1, or 0. Those are my possible outcomes. So I could think of this as a data set instead of just individual numbers. I could list them, all of these in a row, and I would have to list the 2 3 times and the 1 3 times. So the possible values it's more than just 3, 2, 1, 0. It's 3, 2, 2, 2, 1, 1, 1, 0. There's 3 ways to get this and 3 ways to get that, and that is important when you're finding the mean because these ones should be weighted more. You basically have more ways that could happen. So when finding the mean, you basically be finding the mean of all of these numbers, and obviously you could add them up. So you could find the mean by doing 3 plus 2 plus 2 plus 2. And I'm doing it the slow way first because you're going to probably be thinking, I know a faster way to do that. And in class, I would ask you what that faster way is. And then you divide it by the total number of outcomes, which is 8. And I got 12 over 8, which is 1.5. Now notice that 1.5 happens to be in the middle because this is a symmetric distribution. So that's the mean and it's the median because it's symmetric. That should not surprise anybody. You could do this every single time. Sometimes there's so many outcomes you would not want to do this. And so let's talk about the faster way, faster or shorter way, which some of you probably already thought of. Rather than do 2 plus 2 plus 2, wouldn't you rather multiply? I mean, I hope that came to you immediately, but if it didn't, I'm going to take the 3, and I only need 1 3, right? So I would do 3 times 1, plus there's 2's, but there's 3 of them. There's 1's, and there's 3 of those. And there's a 0, and there's only 1 of those. I still need to divide by 8, but notice the 8 comes from the 1 plus 3 plus 3 plus 1. I still get 12 eighths, which is still 1.5. That's a shorter way. Another way of looking at this is to take these guys and think of them as fractions. So now we're thinking probability. The probability of getting 3 heads is 1 out of 8. The probability of getting 2 heads is 3 out of 8, right? So I could take my 3, that's the 3 heads, and multiply it by its probability, and then 2 and multiply it by its probability, and I ran out of space, and the 1 times its probability, and the 0 times its probability. That's another way of looking at this calculation, and that's basically the official formula. This happens to equal 8, this thing on the bottom, but I could think of it as 1/8 and 3/8 and 3/8 and 1/8, and I could do it either way. I could do it with the chapter 1 method, slightly better frequency table method, which I think we did in chapter 1 or 2, or we could think of it as probabilities. So this is basically each value of x, possible value of x, times its probability, and then add them all up. So this is basically what we're doing, and that is the official formula for the mean of a random variable. We'll call it the official formula. It is a population value because we're thinking about all possible flips. So it is the mean, that's the Greek letter mu, of x. It is also sometimes called the expected value of x. And I don't know why, I should probably find out why. Random variables are generally considered to be capital letters, and then specific values of those random variables are lowercase letters. So this is a capital X, and then in the formula, I'm going to use a lowercase x. It's the sum of all the little individual x values times their probabilities. Or in other words, it's the first x value, oh, that's a 1, times its probability plus the second x value times its probability plus all the rest. That's the official formula. In graduate school, they made a big deal out of make sure you have a capital letter here for the random variable, and then values of that random variable are lowercase. I'm not sure that it's quite such a big deal as they said it was, but that's the tradition. So this notation means the mean of the random variable x, and I'm abbreviating random variable. I'm going to do that a lot. Anytime I say RV in this class, it means random variable. E stands for expected value. expected value. In other words, it's kind of like what we talked about with the long run thing in chapter 5. It means if we did this many, many, many times and averaged all the results, this is what we would get. So if they ask you to interpret it, that's what you should say. Or in other words, what does this mean? What does the mean mean? I love it. And you will be asked this in the homework, just to let you know. It is the average value of that variable in the long run after many trials. If I did this many, many times, officially, it's if I did infinitely many flips of 3 coins, the average number of heads would be 1.5. And you should not round this. 1.5 does round up to 2. Do not round it to 2. If you say it's 2, then there's 2 problems with that. First of all, then you're saying it's not here, but it's here, which is wrong. And secondly, you're saying that you don't understand what averages are. So if you insist on rounding it to a whole number, they will mark you down on the AP test. I'm going to put a big note right here saying don't round. There are certain types of numbers that we don't round because it shows that you don't know what it means. The expected value is not meant to be one of the possible values of x. It's meant to be the average of all possible values of x. And if you round it, it makes it look like you don't know what the average actually means. So that's why they will mark you down. All right, so we need to talk about examples of what this is good for. This is actually good for some stuff in real life. So there are 2 major industries that make money off of expected values. And once again, I'm a little disappointed that I can't do this in class because I usually ask people to guess what those industries are. So just think about it while I'm writing this, and then I'll give it away. All right, so the first industry I want to talk about, the people that make a lot of money using this idea of an expected value, is gambling or casinos. So let's think about what they do. They calculate, and they actually hire people to calculate, which is kind of good, the expected value of each game in cash. So let's say they're thinking about blackjack or roulette or one of the other games. They figure out if a person plays it, what possible values they might win and what's the probability of each of those values. And they do this formula. They take each value times its probability and add it all up. And what they get is the average amount that players win after many, many plays of the game. If they know the average value, which is the expected value or average amount people win, then all they have to do is charge people a little bit more than that to play the game. So if people win $5 on average, they might charge them $5.50 or $5.10, or any little bit more is enough to make their overall average profit be positive and not negative. And that is how casinos make money. Every game is weighted just a little bit towards the house winning money or house earning money and the player not. So there are always a few exceptions to that, of course. Some people win big and then a whole bunch of other people lose, and that's where that money comes from. And the casino always wins in the end and makes money. So that's one of the major industries. This is the reason I don't gamble, by the way, because I know too much about expected value. Lotteries work the same way. The state pays out just a little bit less than they take in so that they make money off of the lottery. Insurance is the other major industry that uses this idea. So the insurance industry hires people called actuaries to do these calculations for them. Actuaries, if you love this chapter, you might want to try and become an actuary. Did I spell it right? I think I did. Yeah, anyway, actuaries calculate, again, they calculate the expected value of any major disaster that might happen. So, for instance, what's the probability that your car will be stolen? And then what's the value they'd have to pay you if your car is stolen? And then what's the probability that your car is damaged in a crash? And how much would they have to pay you for that? And they do that calculation so that out of all their many, many people that they serve, they get the expected average or the average value of all those people, value that the insurance company has to pay out, and then they charge you a little bit more than that. Same basic idea. They charge you a little bit more than they expect to pay out on average. And that means in the end, they make money off of all these bad things that happen to people, which is kind of sad. But it's a useful industry. And I'm really glad that it exists because I want to pay my little extra so that in case something bad happens, I'll get money from them. And that's important. So here's an example using the insurance idea because you're more likely to need that than gambling. You're not allowed to gamble yet. You're not old enough. So car insurance. Let's make it practical. 16-year-old drivers, one of the things actuaries calculate is what's the likelihood of a 16-year-old driver getting in an accident compared to somebody older. And that's why they charge more if you're under like 25. I remember when I turned 25, my insurance rates all of a sudden went down. So let's say that they've looked at the statistics, they've used statistics to analyze this, and they found that 16-year-old drivers have a 40% chance of getting in a minor accident. I forgot to say chance. And if they get in a minor accident, the average amount that the insurance company would pay them is $1,000. They have a 20% chance of getting in a major accident. So like the car is totaled and the insurance company buys them a new car, $10,000. And then, of course, 40% chance that nothing bad will happen at all. So that's a possibility. So we're going to find the expected cost for the insurance company of insuring a 16-year-old driver. We find that expected cost by taking each value times its probability. So this 10,000 gets multiplied by its 20%. That's the probability of that. Plus, there's $1,000 and a 40% chance they'll have to pay that much. And then the other 40% of the people, they don't get anything. The insurance company doesn't have to pay them a dime. That's fine. And there's a 40% chance of that happening. So this is major. This is minor. This is no accidents. From the point of view of the insurance company, this is a good deal because they're just making profit, pure profit. And these two, they know they have to pay out, so that's okay. So they know that they have to pay out some. They're going to find out the average amount they have to pay out by multiplying and adding. And this comes out to $2,000. And this comes out to $400. And this, of course, is zero. So we've got $2,400 is the average amount per driver that the insurance company has to expect to pay. And remember, we're only looking at 16-year-olds right now. They would do the same calculation for every age group, and men are different than women, and I've heard that red cars get in more accidents. That they do all of that calculation, and that's what actuaries do. So they're expecting to pay out this much per driver, so they're probably going to charge $2,500, right? For each driver, and let's say this whole thing is per year. So that's the amount that the driver would have to pay for their insurance per year. Some of the people pay this much per year and get nothing. Others pay this much per year and get $10,000 because they got in a major accident. And it all balances out so that the insurance company makes money. And that's basically how insurance works. It's a good deal for everybody because the people who get in the major accidents get the money they need, and the people who don't end up paying for it. But the insurance company makes money off of it, which is good. Last but not least, I'm going to tell you that your calculator will do that same calculation. And I think we talked about this in a previous chapter when we did frequency tables. And I just want to remind you of that. So on the calculator, what you do is you put your X values or your possible values of your random variable into list 1. You put your probabilities or P's into list 2. And then you can do one variable stats and tell it to look at both lists. I'm pretty sure we did this before, but I just need to remind you because it was a while ago. So you can tell it to look at list 1 and list 2 to look at both the X's and the P values. So I'm going to do that with the numbers that we were just working with, and I did not type them in advance, but that's okay. So we have 3, 2, 1, 0 are possible values. You know what? I should do this with the insurance because it doesn't come out right in the middle. Let's do that instead. So I'm going to go back and I'm going to do the 10,000 and the 1,000 and the 0 and the 0.2 and the 0.4 and the 0.4. By the way, you could leave off that last row because if you leave this off, it's 0 anyway, and you get the same number. But I usually put it on just for completeness to make sure I've thought about everything, and that makes it a valid probability distribution that adds up to 100% like it's supposed to. So then, if I do stat calc one variable stats, I'm going to do it wrong first, which is just list 1. And if I do that, it adds 10,000 plus 1,000 plus 0 and divides by 3. That's not what I want it to do. Notice that's not the same expected value I just got. But if I tell it instead to do list 1 comma list 2, or the menu thing looks like this, where I would put my list 1 here and I put my list 2 there, then it does it right and it gets the true expected value, which is 2,400. And that's, another shortcut that you could use, although you should get used to writing this out because on the AP test, they like you to show work. It doesn't hurt to write it out just to prove that you know how. So that is it for these notes. Thank you for watching. This lesson will not be on the quiz. I will say one more thing, which I probably already said in class, but tonight's homework is the Chapter 5 wrap-up homework, and then the homework that goes with these notes is assigned over the weekend. Or I suppose you could do it early if you want to. So I'll see you later. Friday is the quiz over 5-3, and then we'll continue Chapter 6 next week.